In this lesson, we're looking at volume, in particular of cones, pyramids, and spheres. I'm sure in the past you've learned about volume. You probably talked about volume of a square-based pyramid, which would be length times width times height. That's the easiest kind of volume. So any kind of box or rectangular shaped based prism is just length times width times height. But volume is simply the amount of space that an object takes up. So different kinds of shapes can still have volume even if it's not a box. So often we think of volume as something like a bottle, and you fill up the bottle, and that's your volume. And that's certainly one way of looking at it. But if you just look at it as how much space is it taking up, I mean, they go hand in hand. They're not exactly the same, but definitely you get that idea. So it doesn't have to be hollow, in other words. A tree trunk could have a volume. Any solid object you can think of it can have a volume. It's just how much space is being displaced by it. Let's start by looking at cones. So the volume of a cone is related to the volume of a cylinder. And I'm going to say recall, but maybe you haven't learned this before, so I'm just going to talk about this for a second. Think about a cylinder in general. Here's a visualization, a representation of a cylinder. This is supposed to be, it's kind of hard with my highlighter, it's not fine enough, but that end there is a circle, right? I mean, you're supposed to be looking at a 3D picture. So you imagine if this was really a cylinder and you turned it to look at it, what I've just highlighted in green would actually be a circle. And then this circle, and there's another one, by the way, down here at the bottom. So a cylinder is uniform in shape. It's got a circle at each end, and those two circles are the exact same area. And then it's got this space in between. So imagine if you had a circle, you placed it on a desk, and somehow you were able to grow it upwards, it would turn into a tube, right? And that's what a cylinder is. And so think about it. Volume is really just 3 dimensions. If area is 2 dimensions, length times width, or meters squared, things like that, then just adding that third dimension gives you the volume. So if I knew the area of this circle here at the bottom, that again you can't really see, it's a bad drawing, but imagine where that circle would be, and then if I were to just go up from there, that would give me my volume. It would be the same area stacked on top of each other. Imagine a bunch of coasters, a bunch of circular coasters. You've probably seen those that you put your drinks on. You stack them up, and you've got yourself a cylinder. So with that in mind, the volume of a cylinder is the area of the circle. Remember, area of a circle is pi r squared. So it's just that area of that circle, and then all you're doing is multiplying it times the height. So just, again, it's like you're stacking up a whole bunch of circles on top of each other. So that's the volume of a cylinder. So maybe you already knew that, but if you did, well, that's just a reminder. How does a cone compare to a cylinder? Well, again, a cone does have a circle, right? Imagine, whoops, I meant to switch to a highlighter. A cone still has a circle, but it's only got one circle, right? A cylinder had 2 circles. A cone has 1. And instead of going the same width all the way up, it goes up on an angle all the way around until it gets to a point right there at the top. It turns out that the volume of a cone is going to be 1/3 of the volume of a cylinder with the exact same height and the exact same circle area. So again, those two pictures, take a look at them. Imagine that those two pictures, one cylinder, one cone, were the exact same height, and they had the exact same area circle associated with them. The cone is going to be exactly 1/3 of the volume of the cylinder. So with that in mind, all we have to do is take the circle volume, there's the circle volume formula, right? Just transport it over here, pi r squared times h. But now we're going to divide it by 3 because it's 1/3 of the volume. So it takes 3 cones to equal the volume of a cylinder of equal height and diameter. Therefore, a cone is 1/3 the volume of a cylinder. So if it was, imagine now we go back to some empty containers. One's the shape of a cylinder, one's the shape of a cone. If I filled up the cone one with water, poured it into the empty cylinder one, it would take exactly 3 conefuls of water to fill up that cylinder. Okay, so keep that in mind. We'll come back to an example of that later. I believe, yes. Pyramids. Well, a pyramid is, well, again, let's actually not even get to pyramids yet. Let's just start with what I already mentioned. Square-based prism, or a rectangular-based prism. Doesn't even have to be a square, but it will for as far as pyramids go. But any prism, the volume is length times width times height. If we're talking in particular about a square-based prism, that means that that's the top, that's not the base, but the top and the bottom are going to be squares. So if we could make this sort of, so we could see through it, that shape I've highlighted in green would be a square. So instead of having to do length times width times height, since it's a square, that means that the two sides of the base are going to be exactly the same. So this might be the length, this might be the width, but they're both the same, so we'll just call it b for base. And so we only need to know the number once, since it's the same for both of them, and we can call it b squared. So hopefully you get what I'm saying here, that instead of length and width, since length and width are the same, we're just going to call them both b, and b times b becomes b squared. So length times width times height becomes b squared times height. That's the volume of a square-based prism. Now if we take a pyramid that's also got a square base, so again, let's imagine, here's our base, let's imagine it's the exact same base as the one that I drew over, or that you can see over on the left. They both have the exact same size base, and they both have the exact same height, just like for cylinders and cones. There's the same relationship between square-based prisms and pyramids. We just have to take this formula here, base times height, put it over here, and then divide it by 3, because it takes 3 square-based pyramids to equal the volume of a square-based prism with the same heights and same base. Therefore, a pyramid is 1/3 the volume of a prism with the same base and same base shape. So again, that means that if I had an empty box that was a square-based prism, and I had an empty pyramid, and I filled that up with water, it would take exactly 3 of those square-based pyramids dumped into the square-based prism to fill it up. And again, put that aside, we'll come back and look at some, we're just sort of explaining the formulas now, we'll look at some examples in a minute. The last one is the volume of a sphere. I don't have a comparison for this one. It's really just a formula you have to remember. But I can tell you this. Remember, for a circle, so let's try to make this as circular as possible. For a circle, the area equals pi, it's not pi, pi r squared, where r is the radius. All right, so all I need to know is the radius, because pi is a constant number. It's 3.1415, and I never really pay much attention after that. It goes on forever, but those are the first 5 digits of pi. So that's never going to change. So really the only variable I need for the area of a circle is the radius. So it's just pi times radius squared. When you make it 3 dimensions, like a ball, that's what a sphere is, just a ball. Now we have it, it still just involves radius. We're just going to have r there. That's still our only variable. But now we're cubing that. And it's 4 times pi r cubed divided by 3. And as to where the 4 and the 3 relate in, I don't have anything to compare it to like I did for the previous ones. You don't have to memorize it because you're going to have a formula sheet always. I mentioned a formula sheet last lesson, and this is the one, hopefully you found it when you're doing perimeter and area ones. This is the one they give on the grade 9 math test. So you got 2-dimensional shapes on the front of this formula sheet. You've got 3-dimensional shapes on the back. Today we're looking at volume, so we're looking at that last column there. Anyway, so you can always refer back to that when you need to. All right, so that's another formula. So we got all these formulas to use. Sometimes it's straightforward, the question. Sometimes it requires a little bit of playing around with it. Let's see what we can do with this first one. We're supposed to find the volume. It gives us some value s, which is 10 meters, and r, which is 6 meters. Now we know what r is. R is the radius, right? So that's 6 meters. I'm going to put that there. They've given us this, which is 10 meters. That's not part of the formula. If you go back and look at the formula here, it was pi r squared h divided by 3. So that's just, whenever you're working with formulas, it's good to write them down again. Pi r squared h divided by 3. That's volume. So we've got our r, but we don't have h. Instead, we've got something called s. S isn't part of the formula. So how can we get h from the information we're given so that we can actually do the formula? Well, if you're looking at this picture, again, it's supposed to represent a 3-dimensional cone, but you can also see it actually has a shape hidden within it. In a 2-dimensional world, we can see a right triangle here, right? Let's outline it. Let's see what I can do. All right, so there's a right triangle. I sort of covered it up, but you can see that it does have a little box in the corner, and it makes sense that the height is perpendicular to the base, so it should be 90 degrees. So think of that like a little slice. So we can actually, if we know S, I guess I should explain a bit more. S is what's called slant height. In other words, it's the height if you measure from the outside of the base up to the point. So it literally is like a straight line, but on an angle, if you think about it in 2 dimensions. So being a right triangle, knowing 2 of the 3 sides of a right triangle, I can use Pythagorean theorem. And remember, there's 2 versions, c squared equals a squared plus b squared. That's if you're trying to find the hypotenuse. But I'm not trying to find the hypotenuse, that was s. I'm trying to find one of the other sides. So I'm going to use the version that has a squared equals c squared minus b squared. And remember, it doesn't matter what a and b are, just c has to be the hypotenuse. So if I want to find h, so I'm going to replace a with h squared equals 10 squared minus 6 squared. And so we have 100 minus 36, and we have 64, and then we'll take the square root of each side, and h ends up being 8. Now, I've got what I need to fill in this formula. I can go pi times 6 squared, because r was 6, times h is 8, divided by 3. And when I type all that in, I get 301.6. Now, I just had that pre-worked out to save a little time, but you can confirm that. Do pi times 6 squared times 8 divided by 3, and you should get 301.6. So there's the formula, but there's also sometimes tricks. So you can't force things. If they give you this slant height, like in this case, you can still use the Pythagorean theorem to help you out. Find the volume for this pyramid. These words we don't need. I'll get rid of that. All right, so again, what do we have? Well, this time they gave us the base. As we'll use the same colors. Well, we got the base, which is 4, and that's square base, so those two are both going to be 4. And they gave us the height, which is 12. You can see that you can have a slant height for a pyramid as well. This question doesn't force you to use it, but if they did give you slant height instead of, say, the height or the base, then you could use Pythagorean theorem again, just like in the last question, to work out the missing part. But we don't actually need to in this case because they've given us what we need. Remember what the formula was? Let's go back up here. It was base squared times height divided by 3. And they've given us both b and h, so this one's easy. It becomes 4 squared times 12 divided by 3, which will be 64 centimeters cubed. Did I put units for the last one? Because I should have. I should always put my units down. Yes, I did. Meters cubed. So for volume, it's cubic units always. This last one is a sphere, and we only need the one variable. We only need the radius to do that. Remember, the formula was v equals 4 times pi r cubed over 3. And if r is 30, then it's going to be 4 times pi times 30 cubed over 3, which works out to 113,097.3 centimeters cubed. So that one variable to fill in, nothing we have to convert, all very straightforward, so it's a pretty easy one.